The following video aims to explain the concepts of atoms and molecules in the context of chemistry and physics. To begin, the materials that make up our world can be made up of many other materials in combination. Let's consider the example of iron pyrite or fool's gold. Pyrite is a natural mineral that tends to grow in the shape of a cuboid. It is a combination of iron and sulfur, and interestingly has a unique set of properties that the other two don't have. For example, iron is strongly magnetic, pyrite, however, is not. It should be noted that a simple mixture of powdered iron and sulfur will not produce pyrite, because no matter how fine one manages to make the powders, they can still easily be separated with a magnet. However, if we heat these two components, they will appear to change into a massive iron sulfide, of which pyrite is the natural form. This shows that something important is happening when these two materials are heated together. This is referred to as the formation of a compound. Two or more materials have been combined to make an entirely new substance with different properties. The two substances that make up iron sulfide, iron and sulfur, are particularly special in that they aren't made up of any further materials. They exist by themselves. One could refer to them as the most elementary forms of matter, and so they are given the name elements. There are 118 elements currently known. These elements are represented and organized in an arrangement called the periodic table, which is shown in the top right. Examples of elements include carbon, which make up the graphite of pencil lead, the oxygen and nitrogen in the air, or copper found in electrical wiring. These are all examples of pure elements, just one. From this one might assume that a specific element will always have the same appearance and properties. However, this is not true for many elements. Carbon is well known for this, and has many alternate forms called allotropes. Most well known are diamond, graphite, and amorphous carbon. Of these three, only graphite is conductive and only diamond is transparent. Diamond is also very hard and does not easily scratch, making it very useful as decoration on long-lasting jewellery. Conversely, graphite is particularly soft and is used for drawing, as it very easily rubs away onto a sheet of, for example, paper. Why is this the case? To understand this, we must consider what could be happening on the very small scale. There must be a very small part of the material that cannot be split apart into something smaller. This is referred to as an atom. The structure of an atom is more complex, but for now it should be represented here as a sphere. Since the materials are solid, force is required to separate parts from each other. A very large amount of force is required for some allotropes, and not others, as follows. If we zoom in and consider how each atom of these substances is arranged relative to the other, we can see that the pattern is quite different between diamond and graphite. The arrangement of atoms is called the crystal structure. Diamond on the left has the appropriately named diamond crystal structure, whereas graphite is composed of layers of a hexagonal lattice stacked on top of each other. The layers of graphite are spaced quite distantly, and as such they easily delaminate when graphite is struck or abraded. By contrast, diamond has a much stronger structure, with each carbon atom being bound tightly into the crystal structure. To explain the difference in electrical conductivity between these two materials, we must notice that in diamond each atom has 4 close neighbours, whereas in graphite they each have only 3. This leads to the conductivity of graphite. But to truly complete the explanation, we must now consider the finer structure of an atom. An atom is made up of 3 kinds of particles, protons, neutrons, and electrons, which differ by their charge and their mass. Protons have a positive charge, electrons have a negative one, and neutrons have no charge overall. In addition, electrons are much less massive than either protons or neutrons. The protons and neutrons are bound together in a dense location in the center of the atom, called a nucleus. The behavior of an electron is more complicated. They can be seen as existing in regions of space called orbits. However, these orbits are not very similar to those of a planet about a star. Instead, the atomic orbitals are 3-dimensional, with a variety of possible shapes. The electrons cannot be observed as having simultaneously an exact position and velocity. This is called the Heisenberg uncertainty principle. This means that the electrons may not be treated as a particle, and are instead treated as waves, with their properties being described probabilistically. Shown here are various orbitals of hydrogen, with more pigmented regions showing locations of highest electron density, and contrasting regions showing difference of phase. This will be covered in more detail in a future video. As for now, I hope you both learned from and enjoyed this presentation. Goodbye until next time.